All right, so welcome back. We're gonna just finish up a few thoughts about specifying concentration, since that's another kind of thing that I have to make sure everybody really gets. And plus we're gonna add in an extra little twist. The osmolarity is something that you likely will not have seen already in your introductory chemistry class. So we have to kind of extend the idea of concentration from molarity to osmolarity. So let's do that. And then we will start the lab. So specifying concentration. First thing to really make sure people get is concentration. This is a ratio of solute per amount of solvent. Right, so for instance, like the ocean. You know, it's got salt water. It's a certain concentration of salt water. If I have just a little cup of ocean water, I dipped it in and I brought it out and I got like a cup of ocean water. Here's the ocean in general, and here's my little cup of ocean water. Concentration is the same. The amount of salt per volume of water is the same whether I'm looking at a cup of ocean water versus the entire ocean. Yet, if I'm thinking about the amount of salt, there is way more salt in the ocean overall than in my little cup of seawater, right? So concentration is not about the actual amount of solute. It's the amount of solute per solvent. It's a ratio, right? Like again, a cup of salt water or a cup of ocean water or a cup of seawater is the same concentration as the sea, but has way less salt than the sea. So just kind of keeping that in mind. So what are the classic ways to specify the concentration of a solution? You've all been in chemistry.
Molarity?
Molarity, that's one of the classics, molarity. So let's talk about, we're going to be talking about the molarity of solutions all the time. So it is important that you understand what molarity is. Again, by definition, what does molarity mean? How do we figure out molarity?
Moles per liter?
Yeah, it's the moles of solute per liter of solution. So if I said I have 1 molar glucose, and this is how I usually write molar, like an M with a line under it. This would mean for every liter of solution, there's 1 mole of glucose in it, 1 mole of glucose per liter of solution. If I had 2 molar glucose, it would be 2 moles of glucose for every liter. If I had a half molar glucose, it would be half a mole of glucose, right? If I had 0.2 molar glucose, this would be 0.2 moles of glucose per liter of solution. You know, we often use the metric equivalent What would be, if I was going to use millimolar, 0.2 molar is the same as what in terms of millimolar? What does milli mean?
1,000. So
1,000th, yeah. So it's, if I want to go from base unit to milli, I just have to move over 3 units or 3 decimal places. It's going to be 200 millimolar. You know, I'll use these equivalently all the time. You should be able to look at 0.2 molar or 200 millimolar and just kind of instantly in your head know, like, oh, it's the exact same thing. In general, I'll talk more about this in lab, but metric units are going to be the only thing we're really using. So you need to make sure you've got some facility with metrics. So this gets us to the point, though, of mole. What the heck is a mole of glucose? A mole of anything? Actually, they don't really have many good eyes. They got big things to dig. No, not that mole. What is a mole? Somebody's got to know.
Kind of an arbitrary
amount
amount
of substance. It's 6.022 times 10 to the negative 23rd. Number of particles.
So 10,
Six.
not, yeah,
It's the
so,
number of atoms.
so it's
It could be
Avogadro's,
atoms or molecules or just Avogadro's number.
Avogadro's number, which is 6.02 times 10 to the 23rd atoms or molecules, you know, of some element or compound. Right, molecules would be compound, atoms would be element. This is huge number, right? This is 6. It's this many atoms or molecules, a huge amount, because atoms and molecules are really dinky. But in reality, a mole of some substance, this is actually bringing it into kind of the macroscopic world. A mole of some substance is an amount that makes a little pile in your hand in general. So
And
it's,
does the atomic weight of an element equal 1 mole of that element?
exactly.
Okay.
If you want to figure out, well, how do I practically get a mole of carbon? You know, you go onto the periodic table and it's like, you know, for carbon, it's 12 is the atomic mass. This means it's 12 grams per mole of carbon. I look at sodium. Sodium is like 23, which means it's 23 grams of sodium per mole. Right? So if you want to figure out the conversion between the physical mass of something and a mole of it, you just go to the periodic table and there's the number right there. The atomic mass is the conversion. Right? I know in chemistry you've done this in all the stoichiometry. You need to be able to interconvert between mass and moles. You know, in this class, you need to have, you know, some basic understanding of that as well. In fact, we'll be doing a little sample calculation in a little bit. We're not gonna, you know, on your exams, you're not gonna have any full-blown stoichiometry. There's not gonna be any math that you need a calculator for, But there is math that you should be able to do where, if it's just multiplying times 2 or something. So we'll talk about this in more detail in a little bit. So mole, sometimes people think of mole kind of like, a dozen. A dozen eggs is a nice number of eggs that is good for commerce, for buying at the store. It's a mole of some substance is a nice amount to be working with, like in the lab. It's, like I said, a mole of, you weigh out 12 grams of carbon, it's a little black pile of dust in your hand. You weigh out a mole of sodium chloride. How do I figure out if I have sodium chloride, which is a molecule, how do I figure out how much a mole of sodium chloride weighs?
You add up their atomic masses in the same proportion of the chemical formula.
Exactly. So it's going to be 23. So this would become like 58.5 grams NaCl per mole. You just have to look up what's sodium, what's chlorine, add them together, and you get that. So that should make sense to you. You will have, again, on an exam, I won't have you doing this as much detail. On a homework, one of the homeworks coming up, you will have to do some of this. So you do need to understand the relationship between, grams versus moles and how they're related. And so that gets us to molarity, right? Molarity is just the moles of the solute, which you can figure out. You can do the math, figure out how many grams and weigh it out on a scale to make, if I wanted to make a 1 molar glucose solution, I'd have to figure out how much does 1 mole of glucose weigh by adding up the appropriate atomic weights of the carbons, hydrogens, and oxygens. And then I can weigh it out and dissolve that much in 1 liter of water, and ta-da, I've got like a 1 molar solution of a glucose. So molarity should not seem new to you. Molarity should feel like old hat. What will seem a little new to you is the idea of osmolarity. So let's go into that now. It's similar and yet different. From its name, you can get a sense that it's going to have to do with osmosis. In osmosis, when I'm thinking about, we talked about osmosis being the diffusion of water across a semi-permeable membrane, and it's going to be defined, which way the water goes depends on how much stuff is dissolved on one side versus the other side of the membrane. In osmolarity, or I should say in osmosis, the osmotic pressure is going to just depend on how much dissolved stuff is on one side or the other side. It doesn't matter what the particles are. It just cares how many particles on this side, side, what do we call it, side B versus, on side A. If there's more particles on side dissolved on side B than on side A, then which way is the water going to go?
From high to low.
Here on.
So from B to A. Right? No?
Nope. So the colored dots are the particles. So the side.
Oh, I see.
And you're
So,
asking about where water's gonna go?
so
which
the
way-
water's going to go to B to make the amount of particles more similar on both sides. Is that
so the
right?
water is going to, right.
To decrease the
In
concentration.
osmosis, we're going to assume the semi-permeable membrane does not allow the particles to move. They're trapped on whichever side they're already on. So the H2O is going to move towards the side where there's a higher concentration of particles. And like I mentioned last week, you can also think about it. It's kind of like water moving to where there's less water as well. But again, intuitively, I like to think about it as the water moving to the side with a higher concentration of stuff. So the thing that's important here, though, is the water doesn't care what the particles are. It just cares about how much total particles on one side versus the other. So osmolarity is going to be moles of total particles per liter of solution. This is osmolarity by definition. So notice that this is a little, it's similar, but it's different from molarity. It's different because total particles, all solutes. It doesn't matter what the particles are. In molarity, it was specifically the moles of some particular solute. So before I move to the next extension of this, does this make sense? It's just how many moles of total particles per liter of solution. It's similar to molarity, but it doesn't care about what the solute is anymore.
So what you're saying is that when you're trying to find the molarity of something, it might have 2 or 3 substances dissolved in it. And so you find the molarity of each.
So molarity is just going to be talking about one particular solute.
Right, but I'm trying to differentiate between molarity and osmolarity. So molarity, let's just say there's a substance and it's got 2 different things dissolved in it, and you find out what the molarity of each of those things is separately. In osmolarity, it's those 2 things put together.
Yeah, you'd have to see the total amount of it. And so, but even with a single compound, it can get tricky, which is what I'm going to do right now. So if I have let's start with glucose. I have 1 molar glucose solution.
Okay.
That's going to be, by definition, 1 mole of glucose per liter of solution. If I want to make this osmolarity, on the top, I need moles of total particles rather than moles of glucose. The way I like to do this is dimensional analysis. Dimensional analysis is just multiplying times factors that are basically equal to 1. So if I want to convert this, I know I want to have moles total particles on top. I would need to have moles of glucose. Whoops. On the bottom so they cancel out. What is the relationship? If I have 1 mole of glucose, how many moles of particles will be in the water?
Avogadro's number?
Do we need to count how many atoms are in a glucose molecule? Is that what you're getting at?
Now, what happens to a glucose molecule when it goes into solution?
Nothing.
Nothing. It stays intact.
So it's 1 to 1.
It's 1 to 1. If I have 1 mole of glucose, I have 1 mole of particles, because each glucose stays intact as an independent glucose. So it's 1 to 1. So then I can do the math. Moles glucose cancels with moles glucose. This is going to 1 mole total particles per liter is 1 osmolar. So 1 molar glucose is 1 osmolar solution.
So then if you have, let's say, an ionic compound like calcium chloride. so
Here, let's do sodium chloride, since I already got it up on the screen here.
Oh, sorry, I didn't see it.
So by definition, what does 1 molar NaCl mean?
particles of sodium chloride. So
No.
one,
so by
mole of
defi-
sodium chloride over one mole of sodium chloride over 1 liter.
Yeah, 1 mole NaCl per 1 liter. And now I got to do a conversion again to get into moles of particles, but it's going to be a little different. What's the conversion? What, for every 1 mole of sodium chloride, how many moles of particles end up being
2.
into 2? Remember, it dissociates into 2 independent things. So again, moles of NaCl are gone. We end up with moles of particles per liter. This is going to be different. This is now going to equal 2 moles of particles per liter. This is 2 osmolar. So this is really important to understand here. If my compound does not dissociate, then the osmolarity and the molarity are just going to be the same. But in these electrolytes that do dissociate, my osmolarity is going to be greater. You know, if this was calcium chloride instead, what would my osmolarity be?
3.
Be 3, because I get 3 particles for every mole. It would be so triple whatever the molarity is. You know,
Just to make sure I wrote this down right, you said osmolarity will be greater in particles that dissociate.
in compounds that dissociate into separate
Okay.
particles.
Oh, right. In compounds. Okay. I knew I'd written something wrong, but I couldn't figure out where I missed it. Thanks.
So trying to think whether it makes sense to hold on. I have most of the stuff I have in my office at school, but I'm going to try to find something real fast for you. So I'll be back in just a flash.
Hey, class. So since we have like a hot second, I'm just going to ask a clarifying question before he gets back, because I think someone could probably answer this. So for the 2 moles of NaCl, the reason that the osmolarity is higher is because we've got the last step of the conversion there with 2 moles of particle. That's because we've got the Na and the Cl. Is that why we've got 2?
Yeah.
Yes.
Okay. All right,
Because
that's
it does dissociate.
right. So you end up with 2. Got it. Cool. Thanks.
So if it was like NaCl2, it would be 3.
Yeah, perfect. Yeah, and that's why the glucose doesn't, because it stays.
It's CaCl3, CaCl2, NaCl
Oh, well,
is
yeah.
good. Yeah. So, all right. So this is kind of making sense. All right,
Yeah,
the
there-
other type of way to specify concentration, which we can say is percent concentration. This can be by weight or volume. This is a much simpler way to specify concentration. This is the kind of thing you don't have to do math so much. This is just going to be kind of, I should say like grams of the solute over the grams of solution. So you can just be weighing this out. And water, how much does water weigh? It's a really simple.
I just know the pounds per gallon, 8.3.
No, so no,
18 grams per
18
mole.
per take.
no, so we don't have to go into moles here. We just have to have grams. So if I have a volume, I have like, what's the normal metric unit for volume?
Liter.
Liter. And for smaller volumes, we talk about 1/1000th. If I have 1/1000th of a liter is what?
Milliliter.
Later.
1 milliliter. And 1 milliliter, which is also the volume of a cube that's 1 centimeter on each side. So this is also, we call like a cc or a cubic centimeter. It's the same. Cubic centimeter and 1 mil are equivalent. And it turns out that 1 cc or 1 mil has a mass of 1 gram. Which means an entire liter would weigh a kilogram, right? So this is a nice little thing to keep in mind. This is why metric system is so much easier than like gallons and how many ounces in a gallon or a cup or a pint or a quart it's so crazy and weird. When you get to the metric system, it's all pretty.
So you're saying that 1 gram, 1 milliliter of water weighs 1 gram.
Yes. So this is actually a really helpful little thing to remember, because when we go to, I should say, grams of solute, gram solution times 100, because it's going to make it a percent. So if I have grams of solute per gram solution times 100 to make my solution, if somebody says, oh, I would like a 5% glucose solution, I would just have to weigh out 5 grams of glucose, which you could just weigh out on a scale. And I could put it in 100. What would be 100 grams of water?
100 milliliters.
100 mils. 100 mils of water. That is going to be the same as basically 100 grams. I'm done. So mixing up a percent solution is pretty trivial. You just measure out that number and dump it in 100 mils of water and call it a day. So it's a very common way to specify solutions in the real world because it's much more practical. You don't have to do a lot of math and go to a periodic table and convert between moles and grams. You can just stay directly in the world of grams, which is, what you can actually measure for real with a scale. So you're probably all like thinking like, okay, we're going all this. Why do I care? I will show you why this becomes really important right now. So right. So you have like your cells in your body and different fluids floating around them. It's important that the osmolarity of all these things, the fluids inside the cells, outside the cells, it all has to basically be balanced. And if it's not, water's going to go in and your cells are going to inflate and explode, or else they'll shrivel up and turn into little raisins. So as a rule, physiological fluids, whether inside or outside the cells, tend to be around 0.3 osmolar, or 300 milliosmolar is the same thing. In reality, it's more like 280 to 300 milliosmolar. But for our class, let's just make it simple and say 300. So this is a number you need to remember, because it's it's like knowing that somebody's temperature has to be 97 point whatever, or else something's wrong, right? It's a important number about human physiology that you need to use to assess lots of other things. So knowing that all of your body fluids have to be 300 milliosmolar, or 0.3 osmolar, we are now ready to try to make, okay, I'm gonna go, wanna stop this. So this thing right here is an IV flesh syringe. This is what you would clip in. It's got like some saline in it, salt water, and it's designed to jack into the IV line and squish it to kind of clear the lines out. But it's also going up into your veins and mixing around with your blood cells and your blood and all your tissues. So if this is not the exact right osmolarity, instead of helping your patient by clearing out their IV line, you are going to damage them by exploding their cells or making their cells shrivel up into raisins. So this saline, this salt water, has to be what osmolarity to make sure that it's actually doing good for your patient instead of hurting them.
0.3.
It's got to be 0.3 osmolar. But like I said, in the real world, people tend to specify these concentrations as percent. So I'm not going to show it to you quite yet. We're going to do the math instead. I have a question. What percent NaCl, saline, for my IV flesh syringe? Again, I'm trying to kind of show you that all these ideas like molarity, osmolarity, and all that, it's like, it's not just like all of this intellectual stuff to hurt your brains. It's actually going to be really important to actually make sure that you're, doing no harm and actually helping people. So where's my starting point? In fact, someone just said it. What is going to, if it's going to be a liquid, a fluid that's going to mesh with all the other fluids in my body, what do I know about the concentration of it?
0.3 OSM.
It's going to be not 0.3 osmolar. This is going to be my starting point. Not anything else that's true. This has to be true. If it's 0.3 osmolar, then it's osmotically balanced and my cells will be happy. There's not going to be water moving in or out. So by definition, what does that mean? If I want to kind of expand this
0.3
out.
particles over 1 liter of solution.
0.3 in moles of particles.
Moles, sorry.
All right, so that's where I'm starting. But obviously I want to end up with grams of salt per grams of solution. So I'm going to have to end up with grams of salt on the top. So we're not anywhere, we're not close yet. We're moles of particles. So we can get closer to grams of salt by moving into the world of salt instead of particles. So if I do my next step here, how could I convert moles of particles into moles of salt?
Well, you divide it by 2 first, maybe?
So so part of the nice thing about this dimensional analysis is if you're trying to decide, do I divide or multiply? You just have to make sure the units cancel correctly. I want the moles of particles to cancel with the moles of NaCl to stay on the top now. So then I can think, where does the 2 and the 1 go in this thing?
So 2
So,
moles
oh.
particle, 1 mole NaCl. So 1 on top, 2 on the bottom.
Exactly. 1 mole of NaCl becomes, so this is the way I'm going to do it. So now I have moles of NaCl, but I need grams of NaCl if I'm going to do percent. This is going to be grams of NaCl over grams of solution times 100. So how do I convert this now from moles of NaCl to grams of NaCl?
Add their atomic weights.
And so that's going to be, I got 1 mole of NaCl. It's going to be like 58.5 grams of NaCl. Now the moles of NaCl cancel out. And if you does anybody have like a calculator at home right now?
Yeah, hold on just a second.
So it's 0.3 times 58.5 divided by 2.
Mm-hmm.
It's 8.78.
Yeah.
What's
8.78.
So about 8.8, we're going to have grams of NaCl per liter. Now I still got to get this into percent. So I have grams on the top, 8.8 grams of NaCl. That's a good. 1 liter weighs how much?
We just did
One,
this.
oh.
We just talked
1
about that a
gram.
second ago.
So 1,000
1,000?
grams.
It's going to be 1,000 grams because it's 1,000 mils. Now for percent solution times 100, this ends up being basically 0.9% NaCl. Does that make sense?
Yep.
We figured out how many grams per liter, and we said a liter is just 1,000 grams. So you just put it in percent solution, it's 0.9%. And now, if you can, this is always tricky. Heck. Can you read this thing?
Not
No.
really.
Here, I do want you to see this. I'm gonna turn off the virtual background.
I think you need to make your cell, your square is way too small. You need to make,
Oh,
Like-
duh. Okay, I kind of forgot I was still doing that. Okay, come on, here we go, stop share. Okay.
Okay, yeah, 0.9% sodium chloride flesh syringe.
Do y'all see that?
the view is not.
Yes.
Not really full screen, maybe.
Well,
No.
it's not focusing now.
Yeah, I saw it. It was clear for me for a split second.
Yeah, you can kind of see it now. Anyway, so I,
At 0.9%,
what's that?
to say 0.9%.
Yeah, 0.9%, kind of what we calculated out. So the reason why I kind of went through this whole thing is I want you to see that it's not just some intellectual exercise to think about osmolarity. That's the reason why an IV flesh syringe is 0.9% saline. It's because that is the osmolarity that is going to be balanced with the osmolarity inside your body so you don't have your cells exploding or shriveling. If you were going to have infuse glucose into somebody through an IV bag, you would have to do similar math
Yeah.
and make sure though that the conversions would be a little different. It would only be 1 mole of glucose per mole of particles. It would be 1 mole of glucose per mole of particles, and there'd be a different conversion between grams of glucose per mole. But you would still have to make sure after all of the math, you'd figure out what is the concentration of glucose that is
Yeah.
0.3 osmolar, because that's what that's going to be go into the body without causing osmotic stress. So does that all make sense? Right. Okay. So just kind of putting it out there that this idea of osmolarity is really important, and thinking about whether or not something dissociates is really important. If you are going to do the math to figure out an IV for saline versus an IV for glucose, if you don't know that one dissociates and the other one doesn't, you're going to run into real problems, and you're going to have this concentration off by 2. And you're going to really damage this person when you try to infuse this fluid into their body. So it actually makes a huge difference that you understand that glucose does not dissociate and that NaCl does dissociate, or else you're going to infuse the totally wrong concentration of stuff into their body. Right? So I'm trying to make this seem like clinically practical, because it is. If you're not thinking this through, you're gonna really mess somebody up. So anyway, we are not done at all with osmolarity. We're going to be spending next week is just labs all about osmolarity and hypertonic and isotonic and hypertonic and all of that kind of stuff, and calculating osmolarity to different kinds of solutions. And so we are not done with this by any means, but just kind of putting that out there that this is very important and critical to understand. Okie dokie.